All right, guys. Today we're going to discuss in more detail ionic bonding, which is the first type of bonding and perhaps the most complicated, which is why we're going to do it first. Get it out of the way. So the objectives are that we'll be able to describe the properties of ionic bonds and then also write formulas for ionic compounds. So first things first, what are ionic bonds? If you remember the introduction to a bonding period, you'll remember that ionic bonds are just bonds between a metal and a nonmetal, which is formed by the complete transfer of electrons. So it is a bonding that results from the electrical attraction between large numbers of cations and anions. Basically, an electron that already has a significant amount of valence electrons is very attractive to an atom that only has one or two or three. Okay? So as you can see here, in this example, we have sodium and chlorine. Sodium only has one valence electron, but chlorine has seven. This means that chlorine has a really high electrical attraction, and so it's more likely to be able to attract other atoms with fewer valence electrons to it, thus completing its outer shell. So what are ionic compounds? They're composed of metal cations and nonmetal anions held together by an ionic bond. They usually have a large difference in electronegativity, which is just electrical attraction, as stated earlier here. Okay? Although they are composed of ions, which means that you have a negative atom and a positive atom, ionic compounds are electrically neutral because the total positive charge equals the total negative charge, i.e., just like in math, they cancel each other out. So if I have a -2 on one side, I have to have a +2 on the other, and that will give me 0. We'll talk more about that later, especially when we start moving into balancing equations. So in this example here, we have lithium and fluorine. Much like sodium and chlorine, lithium only has one valence electron and fluorine has 7. Remember that valence electrons are the electrons that are located on the outermost ring. Lithium is a metal and fluorine is a nonmetal. In order to bond, lithium is going to completely give up this valence electron in its outermost shell to give fluorine a full shell of 8 because elements are happy or satisfied with either a complete valence shell of 8 or a complete valence shell of 2. So lithium's single valence electron will hop on over to fluorine. Now fluorine has a complete valence shell of 8 and it is happy. This is a smiley face. It looks kind of terrible right here, but bear with me. And lithium is also happy with a complete valence shell of 2. And this is the goal of ionic bonding, to make sure that each element, each atom in the bond has the appropriately balanced amount of valence electrons. So the result would be lithium and fluorine, and the formula would be LiF. We have another example here with magnesium, which has 2 valence electrons, and chlorine, which has 7. Notice that there are 2 atoms of chlorine in this example, and that is because magnesium has 2 valence electrons, but chlorine already has 7. In order for magnesium to fully transfer its valence electrons, it must pair with an element that either has 6 valence electrons or it must find more than one element with 7. And that's what it's done in this case. So it will shed or transfer one of its valence electrons to one atom of chlorine, and it'll do the same with the second. And now again, we have a full valence shell of 8 on these 2 atoms of chlorine, and on this single atom of magnesium. All three of these elements can be happy. The formula would look like this. 1 atom of magnesium plus 2 atoms of chlorine equals magnesium chloride. 2, this subscript, which is what we call this number here, being the amount of chlorine atoms in the formula, in the compound. So what are the properties of ionic compounds? Ionic compounds are salts, which is why sodium chloride, aka table salt, is a salt. They are formed by the complete transfer of electrons. They are made up of metals and nonmetals. They are solid at room temperature, and they have a high melting point, and they're good conductors of electricity. Would anybody like to hazard a guess as to why they're good conductors of electricity? Okay, great. So essentially, ionic compounds are good conductors of electricity. The short answer is because they have a metal in them. The long answer is that they disassociate into ions or they break apart into their individual ions when they are very hot or when they're a solution. And then the broken apart ions conduct the electricity. But really, it's just because they have a metal. Some additional examples of ionic bonds and compounds are aluminum bromide, potassium sulfide, and magnesium oxide, which is what these formulas mean. So the next question is, how do we know how many of each ion we need? We put them into a formula, and each formula has an anatomy. So in this compound, there are 2 bromine atoms for every calcium atom. The Ca is an element in the compound, as is the Br, Ca being calcium and Br being bromine. And this number here, as I told you earlier, is what we call the subscript, which tells you the number of atoms of that element inside the compound. So how do I write an ionic formula? The name is the formula. And the goal is to create a neutral compound, which means the positive and the negative charges have to cancel each other out. The oxidation number of an ion is equal to the charge on that ion. This is what we call the oxidation chart. These are the oxidation numbers. Every element in group 1 has an oxidation charge of +1, +2 for every element in group 2. Our transition metals have varying charges. We'll discuss that later. Group 13 has a positive charge of 3. Group 14 varies depending on whether or not it's a metal or a nonmetal. If the element is a metal, it will have a +4 charge. If it's a nonmetal, it's -4. Group 15 has a negative charge of 3. Group 16, a negative charge of 2. Group 17, a negative charge of 1. And group 18 has no charge. Why? Because they are fully stable, because their valence shells are full with 8 electrons. So how do I write an ionic formula? The first thing that you're going to do is write down the cation and the anion and their charges. The next thing that you're going to do is swap, drop, and chop. Okay? So let's actually do it. Swap is swapping the charges of each ion. Dropping is when you drop the charges to the other elements in the compound. So you drop them down to the ground, basically. And then chop is when you simplify the subscripts if you can. And what that means is that an element has a subscript of 1, meaning there's only one of that atom inside the compound, you don't actually have to write the number 1. You don't have to write a negative sign or a positive sign. You don't need those things. Okay? So we have some examples here. You have calcium, fluorine, and these two are combining to make a compound. So calcium is in group 2, which means that it has a positive charge of 2. Fluorine is in group 1, group 17, which means that it has a charge of negative 1. We are going to swap these charges. Move the 2 to fluorine and the 1 to calcium. We're going to drop them, which means that this 2, which is currently in superscript, will become fluorine's subscript, and this 1 will become calcium's subscript. And then we're going to chop, which means we get rid of the unnecessary. So you don't need the 1. You can get rid of that. You don't need the negative symbol. That's also gone. You don't need the positive sign. So that's gone. And so your formula would look like this over here. Same thing with magnesium nitride. Okay? Magnesium has a positive charge of 2. Nitrogen has a negative charge of 3. You're going to swap the 2 and the 3 so that the 3 goes to magnesium and the 2 goes to nitrogen. You're going to drop those numbers to the bottom so they become subscripts, and you'll get rid of the positive and negative signs because you no longer need them. And now you have magnesium nitride, magnesium nitride, 3 atoms of magnesium for every 2 atoms of nitrogen. And then finally, we have an example here of aluminum phosphate or phosphide. This is phosphide. Phosphate is a polyatomic ion, which we will discuss later. But this is aluminum phosphide. So aluminum has a positive charge of 3, and phosphide or phosphorus has a negative charge of 3. You will swap those charges. You will drop them. And then you'll notice that positive 3 and negative 3 cancel each other out, which leaves you with 0 charge, which means that aluminum and phosphorus don't have subscripts because they've already done the work for you themselves. Okay, so again, swap, drop, chop, let's practice it. An example, we have aluminum bromide. You break them up into their individual ions. So that is aluminum at Al and bromine or bromide at Br. You would also put the charge here. Aluminum has a positive charge of 3, and bromine or bromide has a negative charge of 2. You'll swap those charges. 1. You'll swap those charges. You'll drop those charges, and then you chop those charges. So what does this mean? Aluminum has been broken up into its ion form. Bromine has been broken up into its ionic form. What you'll notice here is that there are 3 atoms of bromine. Wonder why? Because in order to cancel out or make even the charge, for every 1 atom of aluminum with its positive charge of 3, I need 3 atoms of bromine with its negative charge of 1, because negative 1 times 3 equals negative 3. And that means that these 2 ions will cancel each other out. So you guys go ahead and give it a try, writing the formulas for the following compounds. I'll give you about 2 minutes to accomplish that. Great. So that was 2 minutes. These are the practice answers. So this is if this is what you got, then you are a-okay on the right track. If this isn't what you got, then maybe we should go back and look at the swap drop chop scenario and then also our charge chart, which is what this is called, an oxidation chart. Okay? But we're gonna move forward because we have a limited time with each other. And if we need to go back, then we can talk about this in tutoring. So, what are polyatomic ions? Polyatomic ions act exactly like a regular ion, but they're made up of more than one atom. They typically end in ate or ite, and they are whole, so don't break them apart. The best part about polyatomic ions is that they are all on your reference table, so you should have a leg up on knowing what they are, but you should still be familiar with their names, their formulas, and their charges. So if you just want to go look at your reference table, you'll see this chart over here in the corner. And I want you guys to compare and contrast whether or not these compounds here have a polyatomic ion in them using this chart. Again, I'll give you about a minute for this, minute and 30. You can put your answers in the chat. Go ahead. Okay, perfect. So that is your minute and a half. So just going through the list very quickly, we can see that oxide or zinc, neither oxide or zinc are polyatomic ions. If we look for sodium carbonate, you'll see carbonate here. And remember that rule that they typically end with ate or ite. So even just looking at the back end of this compound will tell you whether or not you're dealing with a polyatomic ion. Nitrogen sulfide with a D. Notice there are two elements that deal with sulfur here, sulfur and oxygen, but this is sulfate and sulfite, so it can't be sulfide. But lithium sulfite, there's a polyatomic ion. Magnesium cyanide is a polyatomic ion, even though it does not end in the ate or ite. There are a few exceptions to that rule. Ammonium is one, the cyanide is one, and then the final one is hydroxide, which happens to be our next. Potassium hydroxide. So hydroxide is a polyatomic ion. And then silver fluoride, nope, not on the list. So we can see how easy and quick it is to get through figuring out whether or not there's a polyatomic ion in a compound. Okay? So how do you write formulas with polyatomic ions? It is the exact same as how you write formulas without them. You separate into their ions using your periodic table of elements and the polyatomic ion chart. You put parentheses around the polyatomic ion. Don't touch the inside of the parentheses because polyatomic ions are a package deal. And then you just swap, drop, and chop the charges as normal. So go ahead and give that some practice. Another 2 minutes, and then we are all set for today. All right, so that's 2 minutes. You guys are free to go today. If you have any questions, as usual, you are free to stay after for additional tutoring or help with the concept.